Video here looking at really how we produce light, or how atoms, I should say, produce light, and kind of the ties to the electromagnetic spectrum, and really for most of you this will be an introduction to the electromagnetic spectrum. So first thing, light can be viewed as both a particle and as a wave. So the way the way Bohr thought of light is he kind of thought of it as that particle, that quantized piece of energy. We can also think of light as waves, and when we think of it as a wave, and not a packet or a photon is the fancy word for that, there are some specific areas. So frequency is just how often that wave occurs. So, if I stand at one point, how many waves hit me in 1 second is one way to think of frequency. So like if you think of this line as being 1 second of time, how many waves? So it looks like 2.5 waves per second. Units here are weird. So hertz, the reason why I like to think of it as how many waves hit me in a second is because the more it hits me, the more it hurts. And their units there are hertz. You may see it written out, you may see it abbreviated, or you may see it written as seconds to the -1 power, or 1 over seconds. Wavelength then is just how long the wave is. Wavelength makes sense. You'll see that abbreviated with the Greek letter lambda right here. Looks kind of like the weird upside down Y. So this is the distance from crest to crest, or you could go trough to trough of a wave, and it is just its distance. It's a measurement there. Alright, electromagnetic spectrum made up of a whole bunch of different parts. The part we see is this part right here, a very, very small amount right in the middle. That's the visible spectrum. That is what our eyes detect. The rest of this our eyes don't detect, but as a developed society, we have created things that use all of this. So like our cell phones down here with radio waves and stuff like that. Same thing with like the Wi-Fi signal, kind of in this end of the spectrum, so longer waves. Over here, much shorter waves with high frequencies. These are things that harm us. X-rays, you can't get too many X-rays before. It could have some negative effects, and then radioactive elements that produce gamma rays. Again, gamma rays cause cancer. We actually use them to help cure cancer as well, and then everything in between. So take a second to look at this picture. Notice it has wavelength across the top. You have frequency, so low frequency, high frequency, and then notice the higher the frequency, the higher the energy. So high frequency, high energy, with short wavelengths. All right, important factors to know. All of those waves, no matter which type, travel at the speed of light. You'll see that abbreviated as c. So 3 × 10⁸ meters per second, or 300 million meters per second. Real fast. What I was kind of talking about there a couple slides ago, important facts to know. So higher frequency, higher energy. So long wavelengths, low frequency, low energy, short, high, and high. Two different ways of thinking about this part up here. Same thing. Alright, visible light, only a very small portion kind of right there in the middle. This is the only part our eyes can detect. And we see a rainbow of colors. This is an old slide. Now, scientists do not include indigo in the... Oops, fix this again. Scientists do not include indigo in the rainbow anymore. They said, I'm not sure what the reasoning was, but we now just go straight from blue to violet. So we now have, what, 6 colors instead of 7. So it's just Roy G. Biv, or Biva. Alright, speed of light. It's equal to wavelength times frequency, and this is a constant. So speed of light is a constant. So if one of these changes, the other one has to change, so this stays the same number. So an equation you're going to need right there. C is equal to wavelength times frequency. So example problem. Red light has a wavelength of 700 nanometers. What is its frequency? So if we talk about what we know, so we know it gives us wavelength equals 700 nanometers, and it wants to know frequency. So we know speed of light is equal to wavelength times frequency. I also need to know C, which we always do. C equals 3.00 times 10 to the 8th. And if we take a look at the units, this is meters per second. Problem with this is, well, we're given wavelength up here in nanometers. If I want to use this number in meters, I need to convert. So let's start by doing that. 700 nanometers converted to meters. So quick review here. I want units opposite. So nano goes on bottom. The prefix gets the 1. Up top, nano means 1 times 10 to the negative 9th. Plug this in my calculator, and I get 7 times 10 to the negative 7th is what I get in meters. Nano canceled. Alright, so now that I have it in meters, I can just plug it right into the equation. I like to rearrange the equation, so if I'm looking for frequency, frequency is equal to C divided by lambda, or C divided by wavelength. So when I do my math here, that's what I'm going to do. I'm going to do 3.00 times 10 to the 8th divided by wavelength that I just changed, 7 times 10 to the negative 7th. When I do that, plug it into your calculator. Don't forget how to type scientific notation in your calculator. Use that EE button and divide by 7, EE, negative 7. I get 4 point, and going to sig figs here, looks like 3 sig figs, so 4.29 times 10 to the 14th. Now I got to think about what is it asking for. It's asking for frequency, so my label here is going to be hertz, or Hz. You could also put seconds to the negative 1 for that. But 4.29 times 10 to the 14th. Notice I took it back and put it in correct scientific notation for my answer here. Alright, so we've said before energy is quantized or made of these packets called photons. Like I said though, light is also made of waves. It can be thought of as both. Physicists call this the wave particle duality of light. You don't need to know that. But how this applies to us is this electromagnetic radiation, light, all these different kinds, X-rays, things like that. We can think of this as a stream of particles or photons. And because of that, we can relate this energy to the frequency that we just kind of solved for before. So this, what's the name of this equation? Like Planck's, it has a fancy name for it. It includes Planck's constant, which is h. But so kind of keeping this in mind, long wavelengths have low energy, short wavelengths have high energy. That'll kind of help us, that's how we can figure out based off of its frequency is what its energy is. So this is a number that I will give you on a test. The speed of light I will not. When we are done here, our answer is going to be in joules if it's asking for energy. So example problem, what is the energy of light with a frequency of 1.5 times 10 to the 12th Hz? So we are given frequency. So frequency equals 1.5 times 10 to the 12th. It it wants to know energy. So energy is equal to H times F. Well, I only know F, but remember we do have this constant H. Remember H equal to 6.63 times 10 to the negative 34th. Super small number. 6.63 times 10 to the negative 34th. So now, think about what we have, plug it in, and this one pretty straightforward. We're given frequency, which is in 1 over seconds, H is in joules, times seconds, so our units agree. We can just plug this right in. So energy equals, I'm going to run out of room here, 1.5, right small, times 10 to the 12th, times our times H, 6.63 times 10 to the 34th, negative 34th. Put that in different color so you can see it. Negative 34th. Plug this into my calculator, not forgetting to use the E button. Times 6.63 second EE, negative 34th. I highly, highly, highly recommend that you type this into your calculator as well and make sure you get the same thing I do. Looking at sig figs, we're only given 2 here, so I'm going to round to 2 sig figs. 9.9 times 10 to the negative 22nd, and that's, can't really see it, joules for my answer there with the label. So energy is in joules. Last one, kind of tying it all together, calculate the wavelength of light with an energy of that many joules. Well, if you think about what we have, we know that the speed of light is equal to frequency times wavelength. We also know that energy is equal to Planck's constant times frequency. Well, if I look, it wants to know energy with a wavelength. Energy with a wavelength. 2 separate equations. But I have frequency in both of them. So in your first equation, go solve for frequency. So frequency equals, oops, I messed that up. Frequency equals speed of light divided by wavelength. And then plug that into energy is equal to H times F. Well, if I know frequency equals this, I can do a little math. Solve energy is equal to H times C divided by wavelength. And then just plug your answers in with these constants. So remember that one, 6.63 times 10 to the negative 34th. Plug that in for your speed of light, 3 times 10 to the 8th. And I'm not going to show my work here. I'm running out of room. But I will tell you my answer and see if you can get the same thing. Oops, we are solving for wavelength, so when I'm done, I got to flip my answer around. So this is what it's solved for, but we want energy. So I multiply both sides by wavelength. Multiply both sides by wavelength. And then I need to divide by E to get rid of it on this side. On this side that cancels, but then I also have to divide it by E. What I end up with is wavelength equals H times C divided by E. And my energy was 3 second EE to the negative 19th. What I get is 6.63 times 10 to the negative 7th. And units, I was solving for wavelength. So this will actually come out not nanometers, but just meters for my answer there. And we'll practice more of this, kind of using both equations as we go forward.